bachelor's degree in psychology from the College of William and Mary. He also has a bachelor's of science in systems science and a master's in computer science and software engineering. He holds his doctorate from the University of West Florida, and he is in the Department of Computer Science at the University of West Florida. Take it away.
Today entitled No Warranty Express or Implied, Why Do We Have So Many Problems with Computer Systems That Pervade Our Lives? I would like to start by saying I think this talk is just at least a little bit of a devil's advocate view of things, and I think it worth presenting because we tend to talk in such glowing terms about the future of technology and all this sorts of things. And this is just a little bit of a reality check on the view from in the trenches. So I think it's worth taking a little bit of time to talk about these things, but understand that I am by no means in any way pessimistic about a favorable role of technology in our future. So the agenda for my talk would be as follows. I'd like to talk about computer systems as complex artifacts, perhaps integrated hardware and software systems are, in fact, the single most complex artifacts humankind has ever created. I'd like to talk about our limits on our ability to demonstrate that computer programs are correct, because we have very severe limitations on knowing that our systems are correct, and I'd like to convey that fact to you today. I'd like to talk a little bit about what I consider are truly significant usability concerns with regard to computers. I will give a very trivial example, but it is one among a great, great many examples I might have chosen. I'll then sort of select just from one particular area, which is large legacy systems, and talk a little bit about some of the problems that we've seen there, but I could have chosen issues from any of the platforms that we use, from mobile devices to legacy systems, and there would be equivalent intuition-boosting examples of problems that we have. I'd like to talk a little bit about what we might be able to do about all of this, and then I'll conclude with a bit of a summary. One of the books that came about years ago by a fellow named Fred Brooks was very influential in my thinking. It was politically incorrectly entitled the Mythical Man Month. So, of course, today this would be the Mythical Person Month, if you will. Oh, but before I go forward, I'm curious to know. Yeah, we'll be politically correct about this. Now, I'm curious to know, though, before I go any further, how many computer scientists are in the audience? Well, some understanding of theory and algorithms, data structures, you know, the usual things. So I'm kind of curious to know, maybe half of the audience. Some of this will maybe be a little bit commonplace for you folks. I'm hoping that it will not be sort of inaccessible for the rest. But I'd like to tell you a little bit about Brooks and the Mythical Man Month. The fundamental idea here is that let's say that we are carrying out a civil engineering project in which we're building a bridge, okay? And our project is starting to run behind. So what do? Well, we bring in more people, we maybe bring in more earth movers, we get the trucks cranking in faster with the braces that are going to hold the bridge, and the project speeds up. The point of Brooks' Mythical Man Month was that if you try to crash a software development project, you have people who are behind schedule, you bring in a bunch more folks and you throw them at the project, you actually slow the project down. Counterintuitive. Why would it happen? Because those folks who were previously developing the software are now no longer engaged in developing the software. They are engaged in trying to bring the new folks up to speed, and they stop moving the project forward. So their software tends to operate in its own orbit, completely separate from engineering concerns, generally speaking. Oh, and with regard to accidental and essential complexities, Brooks talked about accidental complexities of software development. These were things such as primitive, not very usable development environments cumbersome programming languages like Fortran, or extremely verbose languages like COBOL. Those of you confronted who know these know what I'm talking about. In the early days, we used to punch programs onto decks of cards. You would give cards to an operator, and some hours later, you would find out whether or not you had a syntax error in your program. So these were accidental complexities because Brooks anticipated that we would overcome these. But Brooks also cited a bunch of essential complexities in the software development process, such as the invisibility of software, the fact that you can have a static listing of code on a page, but that gives you no indication of the actual dynamic performance as the application runs. And in fact, those of you who know, computer programs are loaded into random access memory where they execute, and there's no way to have a comprehensive view of execution state for other than trivial programs. So invisibility, the fact that software is very easily changed, so we can change the semantics of a program just like that. However, although it is very easy to change, it is very, very difficult to know the implications of that change. Software engineers talk about ripple effects of making changes to software, which means I've changed the way this particular piece works. What effects do those changes have on the rest of the program? Brooks enumerated a bunch of what he considered essential complexities that will never go away in the development of software. One of the fundamental things about software is that it is big. So I want to take just a moment today. It's hard to know what big numbers are. What's 10,000 of something? So I put a couple of these here. And so, for instance, there are about 86,000 seconds in a day. So what does 86,000 of something look like? It looks basically like that. These are dots. Okay, so there's 86,000 of something. What does a million of something look like? You will note that these are dots, again, right? And you will note now, I'll start over here, and I will come over this way. So there's that, times 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6. Roughly 30 pages of those. Congratulations, you just saw a million of something. Okay? Hard to get our brains around these big numbers. IBM's OS 360 came out in 1964, a landmark piece of operating system software. It was the first truly multitasking operating system. That means you could load multiple programs into RAM, and you could switch among them. You could switch contexts, as it's called in computer science parlance. And it was comprised of 1 million lines, 1 million lines of assembly language programming. There were 10,000 documented features in OS 360. What was a feature? A feature was an error. 10,000 bugs in 1 million lines of assembly language program. You might ask yourself, why on earth would IBM release a product with 10 million known errors in it? The answer to that question is they did it because every time they tried to fix an error, they would introduce a worse error than the one they were fixing. It was literally as good as they could make it with 10,000 errors. Now, that is to some degree one of Brooks's accidental complexities because they were programming in assembly language, which is inherently difficult for humans. Now we have higher level languages that are still not all that intuitive, but better for human beings. Microsoft Office Suite, it's proprietary software, so we don't know for sure, but best estimates by people in the industry are that Microsoft Office, which is what? Word, Excel, and Access, is comprised of between 30 and 60 million lines of code. So you remember the million dots we just saw? Multiply that by something between 30 and 60, and that's how many statements there are in Microsoft Office. I forget, one of the speakers earlier talked about LibreOffice, which is an open source. Yes, and thank you, Dennis. And LibreOffice weighs in at a very slim and svelte 12.5 million lines of code. So that's only 12.5 times what we saw. And Windows 10, which is clearly not running on this machine, but Windows 10 is comprised of some 50 million lines of code. Now, what does code look like? This is an algorithm. I'm not going to make any effort to explain what all these symbols are for those of you who don't know computer programs. But this is an algorithm that I teach in my data structures class. It is in a general category called dynamic programming. And this algorithm, all this gibberish, by the way, computer programs are essentially non-English symbolic languages. And this particular thing serves a very nice purpose quite comfortably. It's, in fact, quite efficient for its purpose. But it's comprised of 27 lines of code, which is 0.000000054 of the size of Windows 10. So imagine this many, many, many times over. That's what computer software developers deal with every day of their lives. So what can we prove about computer programs? Well, computer programs are based on logic, right? And logic, of course, underlies proofs. Interestingly, many AI researchers are actually majors in philosophy, and they are formal logicians, because logic can be brought to bear in the process of trying to implement intelligent algorithms. Many aspects of computer programs are, in fact, amenable to proof techniques. So I'd like to tell you about the Towers of Hanoi. And I'd, again, take a survey. How many have heard of the Towers of Hanoi algorithm? OK, this is very interesting, and I'm hoping to amuse the rest of you. Towers of Hanoi is actually a fable. So the fable is that there are monks in Hanoi, and they have these 3 little towers, 1, 2, and 3, and they have 64 golden rings. Sorry, I have little black bars that are those are supposed to be rings. It's just you're looking at them from the side, so you're seeing them like this, so you can't see that they're actually rings, but let's pretend they are. Okay. So the fable is there are monks in Hanoi, and they are moving 64 golden rings from the first tower to the third, subject to 2 constraints. They move 1 ring at a time. You can't pick up a bunch of them and move them, because that would make it pretty fast. You move 1 ring at a time, and you can never put a larger ring on top of a smaller ring. Those are the only 2 constraints. Okay? And the fable is the monks in Hanoi are moving the 64 golden rings from Tower 1 to Tower 3, and when they finish, the universe will be over. That's the fable. Okay? I'll come back to that point in a minute. So here is actual computer program code that solves Towers of Hanoi for some number of rings designated by the integer n. And here we have them in the starting position. So let's see how this would work out. It's kind of hard to anticipate unless you've seen this. But we'll get underway, of course, obviously by moving the little ring. So we move the little ring over to post 3. 1 move. Move the medium-sized ring to post 2. 2 moves. Now we'll move the little ring to the middle post. That was a 3rd move. Now we can put the big ring where we finally want it to go. Okay? You can anticipate the next. Yep, the little guy has to go over to post 1. The middle guy in the 6th move goes to the final place. And finally, with the 7th move, the little ring ends up over there. And we have completed Towers of Hanoi for 3 rings. Okay? Does this make sense? Is it not too aggravating for the non-techies, I hope? We could do a study of this, and we would see that 3 rings take 7 moves, 4 takes 15, 5 takes 31. In fact, if we made n into what we call a variable that could take on any positive integer value, then we would find that for n rings, it would take 2 to the nth power minus 1 moves. 3, 2 to the 3rd power is 8, minus 1 is 7. 4, 2 to the 4th power is 16, minus 1 would be 15, and etc. Now, we could then say the complexity of this algorithm is 2 to the nth power. So now let's go back to those 64 golden rings from the original fable. So we said what? When the monks finish moving the 64 rings, the universe will be over. It turns out the fable was wrong, because if we had the fastest computer that we have spitting out millions of moves of rings per second, that computer program would not be able to complete in the time that our universe will be here until scientists project our sun will burn out and our universe will go away. Why? 2 to the 64th power is 18 quintillion, 1.8 times 10 to the 19. Again, a very large number about which it's just almost impossible to conceive. But anyway, we could set up this. This is describing the complexity of that algorithm, and we could prove the fact that Towers of Hanoi is of this computational complexity. I don't want to get any deeper into it there, and I'm hoping this is not overly technical, but we can prove many things about algorithms. We can demonstrate correctness of individual algorithms and small programs quite readily, in fact. I'll give just a little bit more on this, and hoping not to belabor the point, but just an intuition for how proof techniques might work. Weakest preconditions, the least restrictive set of preconditions that ensure some postcondition will hold eventually. So if we had this, if we wanted to guarantee, and this is a trivial algorithm of assigning whatever the value of y is with 5 added to it to some variable total. This is one statement. And let's say that we wanted to guarantee that total was always greater than 5. Well, there are many preconditions that could guarantee that. For instance, if y were equal to 50, 50 plus 5 would be 55, and clearly 55 would be greater than 5. 1,000 plus 5 would be 1,005, and 1,005 is greater than 5. So there are many preconditions that could guarantee or prove this postcondition. The weakest precondition is y greater than 0. So if y is 1, 1 plus 5 would be 6. 6 would be greater than 5. And that is the value that we have to guarantee for y in order for our algorithm to achieve the result of total being greater than 5. Does this make sense? Minimal, trivial example of proving a characteristic of an executing program. More programming code, and then I promise this is the last. This is something we teach in an introductory programming class. It computes the factorial of n. So for instance, 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. This algorithm does that. This is something from what is called the axiomatic semantics, and it is a formalization for how to prove that a loop is correct. The proof for this program in the axiomatic semantics takes 2 fairly densely packed pages. And I promise you I will not bore you with those today. But 2 pages to prove essentially 4 lines of computer program code. So we just don't have scalable formal methods that exist that show the correctness of large programs. And the conclusion, therefore, is that we simply cannot guarantee that large programs are correct. I'm later going to talk a little bit, by the way, about cybersecurity. Very little. I'll be talking more in the final session today. But we can't prove correctness generally, and proving that a program was impervious to security vulnerabilities would be only one aspect of proving correctness. Does that make sense? So clearly, we cannot know programs are secure. Usability is a huge concern, and in my, I can't even recount to you the number of hours I spent cursing Microsoft PowerPoint in the process of producing this talk. And in fact, I think it is a societal problem that we waste so much time trying to get our alleged productivity tools to produce something. And I hope I'm preaching to the choir there, because it's certainly that case for me. But human-computer interface studies in usability have been going on for decades. And in fact, when we got to the first graphical interfaces and we started having menu systems where we could predictably find things under a particular menu, we were making clear strides toward improved usability of computer programs. However, then we got everything to be web-based, and web-based interfaces often have as much to do with aesthetics, with the aesthetics of the website, as they do with the functionality of the website. And any move towards standardization that we were achieving with graphical user interfaces on local machines was just thrown out the window when everything started to become web-based. So usability clearly has declined, even in an age when we have been studying usability for decades. I'll say a word about this. Usability has certainly been impacted by increasing needs for security. I don't know how many of you at home curse your system administrators because there are things that you are forbidden to do on your organization-maintained computers. It just absolutely rips computer science faculty because we don't have control of our own machines. You know, we're not trusted to install a little trivial piece of software we know to be safe. And that is a usability issue for us. But system administrators always have to trade off security, privacy, and convenience. And part of the reason why system administrators enact such draconian measures, right, take away so many privileges, is because the average end user will go for convenience every single time. They will throw security to the wind. They will throw their own, and particularly young folks, it horrifies me the way they are willing to throw their privacy to the wind by posting on Facebook. So people will go for convenience every time, and therefore there is need for pushback by system administrators, but it impacts the ability to use machines effectively. Antivirus software used to just scan for static virus signatures. Now modern software, now modern viruses are polymorphic. They generate variants of the base program, and so typical virus scanning software is just not as effective as it once was. I have to tell you about this. Some of you may recognize this as being part of Desire to Learn e-learning, a learning management system. This is a tiny little example of the thing that makes me want to rip the hearts out of some software developers, given what we know about human-computer interface. So this is a dialog box for uploading a project to a Dropbox so the students can submit their projects. And it reads, drop files here or click below. And it has a nice little upload button there. So you drag a file over here, you put it there, and you click upload. And what does it do? It gives you a dialog box to get a file. You already gave it a file. It gives you a dialog box to choose another file. So you say, no, cancel that. Or let's say that you separately came in and you didn't put something here, and you click Add. What do? You get a dialog box that says you have to put a file up here first, right? So what do? You click OK and that. You drag the file over here, and this time you click that button instead of that button, and you finally upload your file. This is a tiny, eensy little example. You may say, well, yeah, OK, but you'll learn that after a couple of times. But it seems that despite all the effort we have put into human-computer interface design, we still get this in 2017, and it boggles my mind.
It's always humans who make it, right?
Probably so. I'll shift gears for just a moment and talk a little bit about enterprise systems, because we have really, the internet has ushered in a new world with regard to large-scale, enterprise-scale software. Some of the computer folks in here probably know J2EE, Java's Enterprise Edition, designed for doing these sorts of things. Enterprise systems are typically aggregates of multiple systems that before the internet were standalone. So we would have a computer program system here, one there, maybe in different rooms in a building, maybe in different countries. And with the internet, we are enabled to put adapters on different prior standalone systems and make them able to interoperate. Many of these are comprised of, well, some new components, but components that are decades old. And they're retrofit so that they work together over the internet. They often involve a great many layers of software, and you'll remember, none of those layers can be guaranteed to be correct. Got to keep that in mind through this entire discussion. Such systems are case studies in what can go wrong with complex interacting systems. So I didn't know how to call this one, and I'm hoping I'm not going to get sued. But I'm curious, has anybody seen an interface that looks like this? If you are in an airline, an airport, likely to look like that. One of my favorite home improvement stores, just that. You can bet your boots that is a front end on a legacy system, probably based on COBOL, that was probably created decades ago. So here's a typical disruptive problem example. And as I say, I chose legacy systems. I could have chosen mobile devices. I could have chosen any platform you wish. I happen to choose this. And by the way, I'm citing a major airline. I don't know what this logo is. If you do, it was not that airline. This is just a picture I happened to find and was convenient, right? But in the summer of 2016, the airlines were just going great guns. Fuel prices were very low. As I'm sure most of the folks in this room know, they now put a passenger in every single seat on the airline. I don't know how they do that, but they do. So things were going great. In August of 2016, there was a major computer system failure, and none of the backup systems came up. And so it turned out that the systems were down for more than 6 hours. The airline was ultimately forced to cancel 1,500 flights. The system had intermittent problems over the course of several days. And this was just, people sleeping in airports, the airlines having to put people up in hotels, just bedlam and chaos. Some weeks before, the same thing had happened to a different airline, and in the past year, 3 major carriers had the same sorts of things, all almost certainly based on large, complex, interoperating legacy systems. So they range from some that are really quite well maintained to those that really only exist as a code base and data. And in fact, it's interesting to know, well, I said I took this as a particular example, legacy systems. The problem of obsolete user documentation pervades the entire field of computing, as I'm sure you all know. Why is it? You remember one of Fred Brooks' characteristics of essential complexity was the fact that software systems are so easily changed. So now we continually modify the way that a program works, and the documentation for the end user consistently lags behind. So another usability concern that we have today is the fact that it's very, very hard to have fully up-to-date technical documentation on how to use a computer program. Interestingly, I couldn't believe this. I have a software engineer in my department back home who confirmed that this is true. He dealt with a company that only had the executable code for a system. And now what do I mean by that? How many have heard of Java programming language? Java, C, C++. These are sort of human-like languages. So they have English words and everything that we write. But then there is a translating program called a compiler that takes that, translates it into machine language, which is what the computer actually executes. In some cases, companies have lost that source code, and their software maintainers actually have to make modifications to the program for by working on the executable code. They probably have disassemblers that put it into assembly language, like OS 360, you remember? And that's a little bit better, but what did we learn about OS 360? 1 million lines of code with 10,000 unfixable errors. The leaders of some of the companies understood that the Y2K problem, what was that? We allocated 2 digits for the year. Why? Because computer memories were small. So 1998 was just 98. And the Y2K problem was putting 4 digits for the year. A lot of companies with legacy systems said, this is when we can fix the problem. We're just going to migrate to a new platform that's going to do away with all this. Many perceive such a migration as simply too expensive and disruptive. For instance, most of the airlines, my favorite home improvement store where I see a user interface that looks like the one I showed you. And so this is mine. I wrote in the paper about this. Weighing the prospect of a mass extinction event due to a failed, unthinkably expensive migration to a new system, weighing that against the slow death by 1,000 cuts inflicted by maintaining the old system, many companies chose to keep cutting. I won't even get started on cybersecurity. As I say, later on this afternoon, I'll talk about that. So I'd like to talk a little bit about what can be done, but I'd first like to summarize a little bit the root causes that we need to address. And clearly, by the way, I realized as I'm viewing the other talks just how international this conference is, and I'm so pleased that so many of you wanted to come to the United States to see this. But I would say that this is going to be a bit of a US-centric view of problems, particularly with personnel. But these problems are not atypical for many of the advanced economies in the world. But this will be a bit of a US-centric viewpoint, and my apologies for that in advance. It is clear that we have an insufficient and insufficiently educated technical workforce in the United States. We have all of these mission-critical legacy systems that are just getting older and more geriatric and harder to maintain, but again, it is so disruptive to try to migrate them that companies just keep letting the clock tick away on these things. These days, we have a moving target due to the rapid proliferation of IT just absolutely everywhere. You know, the epitome now of cybersecurity problems are executives who want to use their mobile devices with mission-critical data on them, and they take them out and they sit on a park bench and get up and walk away. So the proliferation of devices, and particularly mobile devices, introduces huge new concerns these days. There are, as we well know, a large number of individual and state-sponsored groups trying to exploit system vulnerabilities for any number of different purposes. And I think underlying all this is a relatively naive belief that just throwing more technology at the problem is going to cure it. Multifaceted problems certainly have to have multifaceted solutions. So what about finding talent? The United States Bureau of Labor Statistics, BLS, has a very, very interesting publication entitled The Occupational Outlook Handbook for the United States Economy. This renders all of the major job categories into a taxonomy, right? Starting with jobs, and then a top layer of categories, manufacturing, et cetera, down to, for instance, computer-related professions have a total of 10 subspecializations in the occupational outlook, 10 different major categories of jobs related to computers and IT. They find that there are 1.4 million computer specialist jobs in computer and information technology today. The Occupational Outlook Handbook characterizes jobs by how rapidly they anticipate growth in that particular area, and virtually all of the computer-related jobs have the top category, which is much faster than average growth expected in the demand for talent in those jobs. On the supply side, doesn't look very good, folks. The amount of exposure to computer-related courses is variable in K-12, but is tended to be low. On the one hand, we tend to have many curricula for high school. Oh, by the way, for international folks, K-12 is up. 10th, 11th, 12th are the last 3 years before students would go to university, right? So that's what that is in the United States. Many students, even in their sophomores, juniors, and senior years, the last 3 years before they go to college, have only basic end-user training with regard to computers. So they will train them in the basics of using the Windows operating system, furthering Microsoft's monopoly. Dennis. They will train them in basic productivity, typically a word processor program. There are many curricula that give students little besides that. I mean, we start training for mathematics in elementary school. I don't understand why we wouldn't be generating interest in majoring in computer science in middle school on. But for many of our high schools, they just don't. There are technical high schools that are very good at giving a full slate of training in computer-related fields, but they tend to be the exception rather than the general rule. In the United States, we speak of the STEM disciplines. I don't know if this is an American thing, or do they talk about this in Europe and elsewhere? Science, technology, engineering, and mathematics, STEM. And there have been a great many initiatives to foster interest in the STEM disciplines generally, and particularly with regard to underrepresented groups such as women. And again, according to the Bureau of Labor Statistics, women earn 18% of technical degrees, 25% of the workforce, 11% of tech executives are women. Absolutely pitiful showing. When I started my undergraduate in 1988, 1/3 of the student population was women and 2/3 were men. It was pretty bad back then. Nowadays, it is about 90% men and 10% women. So we went from bad in the late 80s, early 90s to much, much worse now. And we cannot afford not to have participation by this huge pool of talent. Source of the problem is pretty well known. No mentoring and encouragement. Girls get to middle school and they decide it is somehow uncool to be in computer science and they just go elsewhere. And we have to do better than that. And by the way, I was trying to find statistics. I did not find any I deemed reliable, but I think it reasonably safe to say that women in IT leadership in Europe is not appreciably better than it is in the rest of the world. So if we can't develop homegrown talent, our only other choice is to import talent. 4 minutes. Thank you very much. The H-1B visa program provides 65,000 visas per year and 20,000 for people with masters and doctorates. It turns out, though, that those H-1B visas are for all technical fields, including medicine, biology, chemistry, physics, engineering, all of them, when in fact it turns out really that computer and information technology field alone could easily consume all of those. Salaries are pretty sporty for these folks. I'm stunned to see that IBM was an outlier with regard to the average salary, but you'll notice those are very, very nice salaries to get, very, very attractive. Why? Because they get the cream of the crop. Software development techniques have improved, although sometimes programming languages are imposed by the developers. For instance, Apple has required one programming language called Objective-C up to a certain point at which they said, no, 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 we changed our mind. We're going to phase Objective-C out, and you are going to program in Swift. I find that draconian in its own right. There are a lot of times targeted special purpose programming languages really, really do better than general purpose programming languages that are trying to be one size fits all. So we're starting to learn things like this. I don't have time for TIOBE group, but those of you who are interested, the TIOBE community tracks statistics on program language utilization. Java has burst out ahead of everybody else because of Android development, which is done on the Java platform. Software engineering techniques have certainly improved over the years. We now have notions of things such as agile development approaches that work really quite nicely. The Software Engineering Institute at Carnegie Mellon University has the capability maturity model integration, which goes from 1, which is essentially chaos. There is no process whatsoever for creating the software, to level 5, which is a category where it is measured and continuously improved. DoD contractors have to have a level 3 certification to be able to get contracts with the Department of Defense, and that helps things. But there's some question about whether the complexity of the systems we're trying to produce is outstripping the ability to produce complex systems. So I'd like to conclude by saying there certainly aren't easy answers for the problems that confront us as we try to create computer systems today. Legacy systems are genuinely difficult to maintain, but it is horribly expensive and disruptive to migrate away from them, to replace them. Cybersecurity is clearly a pervasive problem and growing. Ensuring or proving software to be correct is doable but not scalable, by which I mean for very, very small, trivial programs, we can do it, but for large, real-world programs, just not feasible. Improving software development practices is evolutionary, but we tend to see these revolutionary leaps in the ambition of the things that we try to do. So there is essentially a disconnect between our improving ability to produce software and the complexity of the software we try to produce. Having a sufficiently talented pool of personnel is a problem, and that is it.